sometimes insert their own defined opcode handlers. No, they introduce new own opcodes. Especially SendGuardian introduces some function caching that works similar to the compiled variables. It's I call it compiled functions. I don't know how it's called internally by Send, but it's actually the same like the compiled variables for function names. So they replace all the call function opcodes with call function by index, and so they just have a number, and then they look up the function pointer in some internal array. The problem is when you don't know about these opcodes, you can't do anything with the opcode array because all functions are gone. You only see some unknown opcode and you can't do anything with it. So you need a little bit of reverse engineering to understand the new introduced opcodes. Right now there are 3 or 4. 3 of them are totally useless. They are just they are never used. They are just some corner cases optimizations that are never used. The most important one is the call function by index one. And you need maybe half an hour to reverse engineer what this thing is actually doing. And after that you know it and you can implement it in your crypto. You can even repair the bytecode array by just replacing this with the original call function opcode and just switching the operand, which is a number, to a string, so that it's directly a function name. And so you have restored an original PHP bytecode array. Yeah, like I already said, a generic unpacker can either choose to ignore these unknown opcodes and remove them, or try to replace it. The problem is when you remove it, you maybe lose the logic of the program because you lose all function calls. Future cryptos might change other bytecodes, and so you will even lose more. So normally you need to reverse engineer this one or these 2 opcodes and handle them in your decryptor. But for now it's very simple because IronCube and the people behind SendGuard, they know that you can bypass their products, and they don't care because they just tell their customers to use obfuscation, and then the customer says, I cannot use obfuscation, and then they say, it's your own problem if you don't use obfuscation. And so they just don't invest much time in it. So at this point, you have the decrypted bytecode and the repaired bytecode somewhere either in the memory or on the disk, and now you have the problem, yeah, this is some bytecode, but now how do I find vulnerabilities in it? And I will try to explain 4 different things you can do with the bytecodes. First of all, you need some kind of user space access to the bytecode, so that your scripts can access the bytecode and read it, parse it, and whatever you want to do with it. And then I will show you how to visualize and navigate within the bytecode. I will show some slide about bytecode decompilation and some automatic analysis you can do on the bytecode. First of all, like I said, you need some way to access the bytecode from within PHP. A PHP application cannot access the bytecode directly. This is different maybe in other languages, but in PHP there's no way to get to the bytecode from within PHP without using some internal memory corruption or some overflow. Within the PHP world, there are 2 extensions to PHP that give you access to the bytecode. The first one is the Vulkan Logic Disassembler by Derek Rittans, and it basically is a disassembler of normal bytecode. And if you patch it a bit, you can even get the original bytecode from SourceGuardian, because SourceGuardian has no execution hooks, so it just hooks the execute function and dumps the opcodes at the execution function, and so you have the decrypted bytecode and can see it and disassemble it. The problem is the disassembly doesn't help you because it's a text, and you would need to to parse the text and then restore some internal structure for yourself so that you can work on it. So Sarah Golleman wrote some different PHP extension which is called Parsekit. In Parsekit, there's nothing else but provide a function that is called Parsekit compile file, and you just call it and it will give you back a PHP array that contains all the internal information I just showed you on the previous slide. It just gives you a PHP array which is an exact copy of the bytecode arrays in memory. So you can work on it. The problem with Parsekit is that, let's say in 50% of the cases it will segfault. In the other 50% of the cases you will end up with some of the bytes with the opcodes correctly decoded, and some of the opcodes are simply wrong decoded because Sarah doesn't work on it anymore, and a lot of the information is just copy and pasted, and so a lot of opcodes in Parsekit doesn't work. But you can use it to get a rough idea of what I'm speaking about. Because of the problems with Parsekit, I developed my own extension which is called ByteDisk, or sometimes ByteKit. It's similar to Parsekit. Actually, it gives you all the features of Parsekit, but it gives you more things. First of all, of course, it gives you the raw opcode access like Parsekit does, but then it gives you also already the disassembled opcode. So you don't need to write a disassembler, you just use ByteDisk or ByteKit, and you get the disassembled opcodes for free. And then, of course, you get a function class list, but this you can also restore from the other arrays. And last but not least, this is the most important thing, it will give you code flow information. You will get for every opcode an array that tells you which opcode lines will be executed afterwards, which will be executed before. And so if you want to create a code flow graph, you can do this with this information very easily. If you're now Googling for ByteDisk or ByteKit, you will not find it because it's not public yet. I will release it within January when I cleaned up the code. Right now it's not public. So what can you do with ByteKit or ByteDisk? The first thing I tried was, the thing is, I hate simple disassemblies, and reading PHP code in disassemblies is very tiring. And I also wanted to create nice call graphs and nice flow graphs. And so I was searching for a way to graphically represent the PHP disassembly. And most of you maybe know BinNavi, and my first idea was to just write a PHP to SQL script that exports the PHP bytecode to BinNavi. For those that don't know BinNavi, BinNavi is a very nice tool to do binary audits, and it will look like this. And this is actually a PHP function within BinNavi. This one is taken from, no, this one is not taken from FluxBB. This one is a demo function, and if you can read the bytecode, you will see that there is a include vulnerability in line, here I can't read it, but if you see the second box from bottom, there's an include of a variable, and this one is actually a function parameter. So if you call the function with the untrusted user input, it will include an arbitrary PHP file, and you can execute any code you want. I will come to this later. Another thing you can do in BinNavi is to look at the call graph, and in the large window you see a very small part of the call graph of this FluxBB, which is a port of a fork of PunBB, and in the upper left corner you see the complete call graph, which is a little bit complicated. This is the strange circle thing with a lot of dark lines, and every line is a call. And so you see sometimes PHP applications have very complicated call graphs too. Yeah, but so much for the visualization. The next thing I worked on was PHP decompilation. And I heard before that there are some non-free PHP decompilers, but I never knew how complicated it would be to decompile PHP code. And there was nothing public, and I didn't know anything about PHP decompilation at all, or decompilation at all. So I was just searching the internet for papers and came up with this reverse compilation thesis of Cristiana Cifuentes, which is maybe the most, maybe the well-known paper about decompilation. It's quite old, but I just read it and realized that everything in there can be used for PHP bytecode, and you don't need much more than what is in this paper. So the implementation of a decompiler for PHP was very straightforward, and it mainly consists of graph structuring algorithms, and after you have structured the graph, the code flow graphs of the functions, you can create PHP code from there. To show you how this looks, is on the left side you have the code flow graph of some PHP function. You see there are different colors for different parts of the graph, and actually these different parts of the graph are graph intervals. And the idea is to use graph intervals to find loops and to find nested loops, and the way you do this is you first find the intervals of the graph, and then you collapse every interval to an own node. In G2 you see that every one of the 4 intervals of the first graph is collapsed into a single node, and the edges between the intervals are now the edges between the nodes of the second graph. And you do the same again. You end up with G3, and you do the same again, and you end up with G4. And this is very good because it's a single node, which means the graph is not irreducible. This means you can create a very good disassembly from decompilation of it. If you have 3 or more, if you cannot reduce more than 3, because they reference each other, so you cannot reduce them anymore, then you have a problem. This usually is when your language supports Goto. Once the language supports Goto, you cannot create a nice decompilation anymore, because then you need to insert Goto statements, and sometimes you cannot know if you need a Goto or if it's a normal while or loop or something else. With PHP 5.3 there will also be Goto in PHP, but the thing is you will still not end up with irreducible graphs, because the thing with Goto in PHP 5.3 is that you can only jump out of control structures. You cannot jump into control structures, and so you will not end up with irreducible graphs. The next thing, okay, now this means actually that you have detected 2 loops in the PHP function that are nested. So after detecting the loops, you want to detect all the if statements, and therefore you just look at every node that has 2 follow nodes, and then you try to detect if it's an if then or if then else. And you do that by just checking if you do that by checking if the follow node of one branch is actually the other node that was branched in the other way. If this is the case, then it's an if then. Otherwise, it's an if then else. And when you do that, you ignore all the loop heads and tails. So because they already belong to a different control structure, and you don't need them anymore. The last thing is that you detect compound conditionals, which requires PHP jump change elimination. Otherwise, the algorithm doesn't work. It's not so interesting, actually. I'm running out of time, so I will try to speed up. The thing with PHP bytecode decompilation is that it benefits very much from